Welcome to Dr. Jed's continuing video series on calculus. Today's lesson is section 3.4 from Rogowski, rates of change. Now, a rate of change is another way of talking about derivatives, or tangent line slopes. Specifically, though, we want to talk about what we mean. We'll get a couple definitions, then we'll give some examples. An example from motion, the height of an object as it moves up and down. Then an example that might be more relevant is snowfall, approximating from a table. And then an example from economics, a marginal cost example. So, first the definitions. We've talked about it before, but the average rate of change is the amount of change in the y variable, the function f of x or f of t or whatever, over the change in the x variable. It could be x, it could be t. It's the change in y over the change in x, delta y over delta x. It's an average. It's 2 points on the curve. You measure where it is at one spot, you measure where it is at the other spot, and the rate of change between those two is the average rate of change and is the slope between the two. Hence, it's a rise over a run. Instantaneous rate of change is the same idea, but instead of 2 points, we move the one closer and closer and closer to the one we really care about. It's the limit as the delta x goes to 0. So instead of delta y over delta x, we get a dy over dx, which that's Leibniz's definition of the derivative. So this is just the derivative. And that's why it's useful to talk about it here. Derivatives allow us a way of measuring instantaneous rate of change. We have formulas, so it's easier. The first formula that we're going to use has to do with the height of a ball. Suppose we throw a ball, and at t seconds, this is its height right here, in meters. So it's starting off pretty high up. At time 0, it's at 120 meters up. And you're throwing it at a speed of like 63 meters per second. But now, this is gravity pulling it down. This formula is the height at any given time. So what's its instantaneous rate of change? Well, the change of a position is a velocity. So how do you do it? We take the derivative. Instantaneous rate of change is a derivative. So the derivative of this, we bring the 2 down, multiply in there, we get minus 9.8t plus 63, and then what happens to the 120? It goes away, because where you start has no bearing on how fast you're moving. Now the units of this are going to be interesting. This is going to be in, what is velocity? It's a speed. It's meters per second. If you think about it, it's the units of the y divided by the units of the x. Hence, it's a dy over a dx. What is the velocity at time t equals 5 seconds? V of 5 will equal h prime of 5, which is this. We'll multiply a 5 in there. We just put 5 in for t. Now, if you do that, you get minus 49. Add the minus 49 to this, and you're going to get 14. Plus 14 meters per second. So which way is it going? It's still going up after 5 seconds. You could calculate when does it stop going up. That would be when its velocity is 0. How long does it take to hit? Well, that would be when h is 0. There are a lot of kind of problems you can work on with this. But let's move on to another one. Suppose we're going to measure snowfall and rates of change of snow. How fast snow is falling. So for example, from a table, which I'll show you in a second, how fast is the snow falling at 3:45 in the afternoon? Perhaps in the morning, depending. AM, PM, doesn't really matter. Here's our table. Here's our table of snow values. These are in inches. This is time. So how are we going to measure this? Well, we don't have a function. We don't have a formula to measure and take a derivative of. But when you talk about a rate of change, you get average rate of change. And if the average rate is close to the center, we get close to an instantaneous rate of change. So at 3:45, which is right here, we might have something right above. We might have something right below. So let's take a look at the two like that. From 3:30 to 3:45. What's the rate of change? Well, the average rate of change from 330 to 345 will be, well, it's the change in the h, the amount here. So it's 1.2 minus 0.6 divide by, well, the difference in these two. What's the difference in these two? There's lots of notations. 15 minutes. And I'll put units there. So we get 0.6 inches divided by 15 minutes. You have to decide now, what are the most useful units? Do we want to talk about inches per minute? Probably not. Excuse me. Inches per hour is probably a better way to do this. So what part of an hour is this? It's a fourth of an hour. So how much would this be in translating to terms of hours? We multiply the bottom by 4 and the top by 4. So this is 2.4 inches per hour. On the other hand, the average rate of change from 3:45 to 4 o'clock would be, coming back to here, 1.6 to 1.2. Over 15 minutes. So we get a 0.4 on the top. Using the same idea, we're going to get 1.6 inches per hour. So how does that help us? Well, if these were dramatically different, if they were really a huge amount different, we'd wonder if something happened in the middle to change it radically. But given the data, if it's sort of smooth, then we can assume in between it's just generally changing approximately the same amount. So here's one right below it, here's one right above it. So the instantaneous rate of change is going to be about the average of these two. And what's that? The average of that is, oops, I'm sorry. The average of that would be divided by 2 here. So we get about 2.0 inches per hour. So right about 3 o'clock, right about 3:45, it's falling about 2 inches an hour. Does that mean it fell 2 full inches in that hour? Look back. Well, in the last 45 minutes it was only 1.2, and in the next 45 minutes it turns out to be only about 1. So probably not. It's not that it 2 inches falls in the hour. It means that at that time it's falling down at a rate that if it continued at that rate, it'd be about 2 inches in the next hour. But of course the storm doesn't last quite that long. Let's do another example. This one from economics then. Marginal cost. Now marginal cost is something that's defined in economics. It's the amount it costs to produce the next unit. So the marginal cost for X, the amount it costs to produce the next unit, well, produce one more unit, how much does that cost? Subtract off how much it cost to not do that. So the cost for X plus 1 units minus the cost for X units. That may not look like a rate of change. But if I look at that and I rewrite this as C of X plus 1 minus C of X over X plus 1 minus X. Now what's that? The bottom is just 1. So these are the same thing. That's an average rate of change. An average rate of change is sort of like instantaneous rates of change. They're close. And instantaneous rates of change are derivatives. So the marginal cost is sort of close to the derivative. This is not the same. It's not exactly the same. Some people actually count the derivative as the marginal cost, but we're saying they're approximately. We'll use them interchangeably. We'll say they mean the same thing, but they're not quite the same. However, this one's actually easier to calculate than this one. Once we have formulas for this, this is easy to calculate. So let's give an example. Here's the formula for cost to produce X goods. There's a startup cost of $8,000 that you just had to pay out. Then 14.25 per good minus, now this becomes more complicated. As the number of goods increases, this grows faster than just linearly. Minus 3.10 times X to the 1.5, and then plus a little bit at a quadratic rate. So what is the marginal cost? Well, it's going to be the cost at 101 minus the cost of 100. Plug 101 into this. Plug 100 into this. You'll find it's very messy. Or we could say it's approximately the derivative of that. Now, what's the derivative of that? Well, the derivative of this at 100, find the derivative. The derivative is going to be the derivative of a constant is 0. The derivative of the next piece minus the derivative of the next piece. We multiply the 1.5 in here. So multiplying by 1.5, you're going to get 1.55, so you get minus 4.65 x to the subtract 1 power, plus, bring the 2 down, you get 0.08 x. Now, that at 100 is not hard to do. Let's do it. That's 14.25 minus x to the 0.5. What is that? That's the square root. And what's the square root of 100? It's 10. So this times 10 minus 46.25, 46.5. And then x is 100. So plus 8. Now what does this say? We add that all together. We get 22.25. We get a minus 24.25 per good, per unit. What are the units on here? Dollars per unit or whatever it is. Monetary cost per. What does this say? Interesting, it says actually, not that nothing costs, but that actually it, on average, producing more here for a short duration is cheaper. If you only want 100, it's actually a little bit easier to produce 101. That's not very sensible. It should probably cost something. This is a made-up function. It's not based on an actual financial model. Real financial models, this probably wouldn't happen. But this should illustrate how you do it. And that's all we have today. Until next time, I hope your calculus is easy.